Hello everyone. Super excited to be here. I'm Alex, and today we are going to talk about multi-partition transactions in Accord. And I would particularly want to focus on the implementation details and ones that can be useful for developers and operators, so that we could build collective understanding of this project and start preparing for its rollout. It's been a little over a year since I started working on Accord, and I started with the transactional recovery and the journal replay, but gradually got exposed to various other parts of Accord, and I think that by that time I was able to touch most of it, including Cassandra integration. And during this journey, I learned a lot about Accord and would like to shorten your way with Accord by sharing my experiences. And I will start by giving a very short overview of the paper itself, and then try to compare the paper with the implementation. There are many concepts in the implementations that were not covered in the paper at all, but I feel like they comprise a large part of what you're going to be interfacing with. And many of the things I've had to interact with are not present in the paper at all, but I think it's natural for the project to evolve this way, and it's just that I wish these things were described somewhere, so I'm going to try to fill this gap. So I did my best to prepare a collection of talks which cover the things which may overlap with this talk, and would like to keep this skip over some of them. So for the ACID properties like a transaction, multi-partition transactions, check out Mix 2023 talk. It covers Accord and how we achieve ACID guarantees. And for comparison with the LWTs, check, and actually not just with LWTs, but also with other consensus protocol, check out Scott's talk last year. It provides really good analysis. This also covers trade-offs between Accord and existing solutions. And for practical integration details, today's aerial presentation will give you a lot of details about CQL integration. And finally, for the theoretical foundations like FastPath, generalized taxes, and some other things that underpin Accord's design, check out Benedict's talks. And they explain very well how Accord achieves performance contrasted with like the other protocols, and also how we evolve on top of our Paxos implementation. And rather than duplicating effort that was put in these talks, I'll focus on the things that are unique to today's presentation, and we'll hope that it will give us more time to dive deeper into these things. So let's first get a very rough overview of the Accord paper itself, and try to contrast it with the implementation, or see how the implementation actually achieves what the paper is talking about. So Accord is a leaderless consensus protocol, which means that any replica can coordinate transactions instead of electing leader, and it uses a timestamp-based ordering to decide transaction execution order. So the protocol's FastPath completes transactions in a single wide area round trip under normal conditions, and when round trip here is only the surface part though. So that has to be done before we are responding to the user. However, there are more steps that the protocol itself is executing. It's just that we do not have to block upon them for the user to get the response. So Accord can reconfigure its quorums in response to failures, which is a pretty unique thing with Accord. And basically when some of the replicas fail, it can adjust the quorum size to keep the FastPath working. Other leaderless protocols often lose the ability to execute the FastPath during the failure scenarios. So non-conflicting scenario transactions can be ordered independently, which means that we do not create contention if there is no need to coordinate between the keys. This helps with the throughput as the load is increasing. And the protocol provides a strict serializability isolation with real-time ordering. So if transaction A finishes before B starts, they will be applied in exactly that order across all shards. So the fast path. Majority of the transactions in a core can take the fast path. In other words, we can skip the accept phase and go straight to from pre-accept to apply. I will also show it or try to make it more visual or intuitive. Fast path electorates are configurable, but for the purpose of this talk, let's just assume that it's going to be a full replica set. So the coordinator sends a pre-accept with a transaction and a timestamp T0 to replicas across all relevant shards, not just one shard. So it's not single like group of nodes, but several potentially groups of nodes. Each replica checks if this timestamp is higher than any conflicting transaction timestamps that they are aware about. If it is, they accept. If not, they counter with a higher timestamp that could potentially work. The key is to get fast path quorum agreement for every shard that at that original timestamp that we issued the transaction with. If we happen to be able to do that, then we're done. So the transaction commits at T0 and moves to the execution. There is no accept round needed. Replicas also send back the dependency information during this process. These deps tell us the execution ordering, which transaction need to be run in order for us to keep the things consistent. When there is no heavy contention and timestamps don't clash, you get single round-trip latency. When conflicts do happen, the protocol falls back to the full accept phase. The nice thing, though, it is not like all or nothing. Each shard makes its own decisions about the fast path, and some shards might accept T0, while others will need to sort of like go through the full protocol, and this works absolutely fine. So there is nothing wrong with that. Cutting from 2 rounds to 1 can have your commit latency in the common case, and since a core maintains strict serializability, regardless of which part you take, you're not trading anything by getting to the fast path, so it is not a sacrifice. I tried to make it more interactive and made a small tool that can record all of your Accord interactions in either NGVMD tests or Accord burn tests, and give you full lamp or diagram that you can sort of like play with and get deeper understanding of the Accord protocol. I will move to the demo later if we have enough time, because I think that the presentation is going to be so packed with the information that we may actually not get to it. But if you're interested, also hit me up either later today or during some other day, and I'll show you what it's about. So when the fast path fails, Accord transitions to the medium path or slow path to resolve conflicts and achieve consensus. So fast path failure occurs when some replicas propose higher timestamps than the original one due to some conflicting transactions. This indicates that the concurrent transactions have created dependencies that require the execution timestamp to maintain strict serializability. If we receive insufficient responses during the initial phase, we also may take something called medium path. This ensures that we gather enough replica participation to make safe decision for the consensus, and even if some nodes are slow or unreachable. So medium path provides a fallback that maintains correctness while achieving reasonable performance when optimal fast path isn't responding quickly enough. The coordinator applies the hybrid logical clock ordering by selecting the timestamp after all of the timestamps from the given responses. And this ensures the final execution timestamp is sort of like high enough to respect all the observed conflicts and dependencies across participating replicas. During the accept phase, we send accept messages to a simple majority of each shard, which is contrasted with a larger number of nodes during the fast path. Replicas return updated dependency based on the final timestamp, and now that the execution time is established, each replica can provide the precise dependency set that applies at timestamp t, ensuring the order of the transaction. And here you can see the execution of this little path and the dependencies being returned. So you can see that contrasted with the previous, like shorter, like two-phase execution, where you simply have pre-accept and apply steps. Here you have pre-accept and accept, and the further steps such as like apply or commit are followed by that. And you can also see that there are dependencies that are given by the accord accept rep response in the right-hand part for you. So let's walk through the distributed transaction protocol execution flow. So first, we have a commit phase. So the coordinator sends a commit message containing the transaction, timestamp, and dependencies to all the replicas. That establishes that the transaction is ready to execute and ensures that all replicas have necessary information. Then we have a read phase. The coordinator issues read requests to replicas of each shard, sending transaction, timestamp, and shard-specific dependencies. Replicas wait for all dependencies to commit and for lower timestamp dependencies to apply locally before executing their portion of read operations. And then we have result computation. Coordinator collects all the read responses, combines them, and executes the transaction logic in order to get the final response. And finally, the coordinator sends the apply messages containing like transaction, timestamp, dependencies, and computed result to all the replicas, and then result is returned to the client. Or actually, a result can be returned to the client before the apply phase, so this is not entirely true. It is important to draw a distinction between commit and apply. Commit establishes consensus that the transaction will execute, while apply actually executes the transaction with the computed result. This separation is required due to dependency resolution. Other transactions can sort of like depend on ones that were already committed, but not yet applied. And here you can see sort of like a full accord execution graph. So you also have pre-accept, followed by the accept, and followed by the commit, and interleaved with read requests, and so on and so forth. Again, I hope that this sort of like gives you a rough overview, but in order to get a more tactile feeling, you can sort of record it on your own cluster and play around with the tool and explore the accord states more visually. Now let's talk about the building blocks that make accord implementation work. Messages are the unit of communication between the nodes. These carry protocol information like pre-accept, accept, commit, apply, requests to coordinate the transaction execution. Commands represent the unit of local metadata for a particular shard. Each node maintains command objects that track the state and progress of transactions within the particular shard's responsibility. Transaction ID is a transaction identifier built on top of hybrid logical blocks, providing globally unique identification that also has real-time components, so you can know when the transaction has executed. This ensures that every transaction has a distinct identity that maintains causal ordering. So topology captures immutable metadata of snapshots that require that define or tell us about the data ownership. This tells which nodes are responsible for which data ranges at any given point in time, and it's also versioned to handle the cluster changes safely. Dependencies represent a transaction dependency relationship that determine execution order. These dependencies ensure that transactions execute in the correct sequence to maintain the consistency guarantees. And finally, participants, as contrasted with dependencies, define the keys and ranges that a particular transaction touches. This determines which shards will need to be involved and helps route requests to the appropriate replicas. Now, let's take a look at the subsystems in Accord. Topology and config service, they manage membership and ownership metadata. They track which nodes are part of the cluster, which ranges each node is responsible for, handling changes as the cluster evolves. Journal provides state persistence across restarts. It ensures that transaction metadata survives the node failures and bounces and enables nodes to recover to a consistent state. Progress log coordinates forward progress and recovery. Here, I think that the word recover is a little bit overloaded because I keep saying recover in different contexts. So in journal, recovery means that we retrieve something back from disk. And here in progress log, recover means more something like pick it up because we think that the previous coordinator has failed. Progress log tracks transaction advancement and orchestrates recovery when the nodes fail or fall behind, and it ensures the forward progress or liveness in more theoretical terms. So durability service ensures that transaction durability across shard and like replicas are ensured, or it sort of like establishes it. It manages the guarantees that committed transactions are safely persisted, and it plays a crucial role in garbage collection and transactional states. Without it, we wouldn't be able to expunge the entries from the journal, and I will try to demonstrate how specifically we're doing it in a couple of slides. And command stores act as sequential executors, and they manage per shard metadata. Each shard is its own command store that processes transactions in order and ensures the straightforward and consistent state transitions. So this is my attempt to make it easier to see and understand what a core cluster may look or feel like. So every horizontal line here is a node. Within the node, we have a bunch of command stores. And these command stores represent shards. And within shards, we have transactions, which are identified by their ID and the current status of the transaction. And you can search by transactions and by transaction ID and sort of try to understand which specifically transactions are or where the transactions live. If you can also click inside of the transaction or try to zoom in to the transaction and inspect the state of the transaction themselves. Here, the nodes are vertical lines. I thought that this representation is going to be sort of more intuitive, and each command store is sort of its own box. So we have same transaction that is executed across several nodes, but also on several nodes, it is executed on several shards. So transaction can live both on different nodes, but also different parts of the transaction, because it's a multi-partition transaction, can be executed on different shards on the same node, right? Each shard will do its own bookkeeping, and commands are moving between states by coordinator and sending messages to all the replicas, and replicas routing the messages locally and executing them on a corresponding command store. And command store itself executes coordinator requests sequentially, always sequentially. So this helps you to reason at least about local execution quite trivially. So let's take a closer look at command stores, which are, as I mentioned, sequential transaction metadata managers for each shard. So command stores store command state and execution metadata locally. So this is not when I'm talking about command store, I'm not talking about user data, which is sort of natural to think about whenever you talk about eventually consistent requests. But this is transactional metadata, which means that the information about the transaction itself. So command stores maintain the complete lifecycle information for every transaction that touches their shard, and several auxiliary collections that facilitate quick access to metadata on the hot path. Command stores provide exclusive access via safe command store wrappers during execution. And when you see safe prefix in a core class, you know that it is intended for you to interact with. For example, you can see an update to, or you can issue the update to a command state via save command store, or if you have like commands for key and you would like to update it, you're going to be interfacing something called save commands for key. So to update the commands, you use save command store, and to update commands for key, you use save commands for key, and so on. So since I already mentioned the commands for key, this is a collection that maintains per key transaction histories for dependency calculation. When new transactions arrive, commands for key can quickly determine which existing transactions the common transaction must depend on, and it tracks the ordered history of the command for each key that this transaction has touched. This enables dependency calculation during a pre-accept phase and supports pruning of old metadata once transactions are no longer needed for dependency resolution. So command stores are also coordinate with the journal for metadata persistence, because we do need to save every single thing that has happened in the command store in journal, and with the data store for state application. The journal ensures durability of transaction decisions, and data store handles the actual reading and writing of the application data, as we do in the regular eventually consistent Cassandra read-write path. And finally, command stores interface with something called progress log to ensure forward progress. Once a transaction goes through the command store, progress log is notified of the change and will monitor further changes to help detect and resolve situations where transactions might be stuck waiting. This ensures that the system maintains liveness even if coordinator goes down or cannot keep up with the coordination due to other reasons. And now we finally move to auxiliary collections maintained by command stores. And I think that one of the most important ones is called redundantBefore. So redundantBefore tracks time-bound or time-bounds, plural, that mark when transaction metadata can be safely discarded from journal. When a transaction becomes redundantBefore for a certain timestamp, it means that no future transactions will need to reference this transaction or all transactions before it for dependency calculation. This enables garbage collection of all command metadata while preserving correctness. The system can delete commands that occurred before this redundantBefore timestamps without affecting any future transactions. RedundantBefore is generally made by redundantBefore is generated by the durability scheduler, and it plays together with the data store, specifically with the man table flushes. In other words, transactional metadata state has to be kept around until it is universally persisted in a stable storage, not just metadata storage, which means that having it in journal is good, having it on the node locally in SS table is great, but having it universally, like on each and every node in their SS tables, is the thing that we would like to ultimately achieve. The redundantBefore mechanism tracks timestamp boundaries across different system components and replication levels, and properties like locally redundant, locally applied, pre-bootstrap, all of them represent different stages of when specifically data becomes safe to discard versus like locally versus globally. So for example, a transaction may be locally redundant, safe to remove from the node's memory, but may still be needed for other replicas to finish their application. And I tried to visualize it by having an ability to select a particular locally applied or other states and having the transactions being grayed out. If they're grayed out, then they are safe to remove by a specific property. So that means that certain transactions on this command store can be expunged, at least in principle, and if like certain states were achieved, they can be completely eliminated from the journal and garbage collected. And now let's talk about dependency tracking. So a cord carefully tracks and distributes dependencies. And primary mechanism for this is commands for keys and responses to pre-accept and accept, and some other phases where the depths are determined and notified about. So I thought that the quote from Neil Stephenson, Anathem, is mandatory here, so I included it. Each command has dependencies, or can have dependencies in principle. It might be waiting on, either on the same shard or across the shards. It may happen that dependencies go several levels deep, and command might be waiting on a command that is waiting on a command, and so on and so forth. And commands for key that I have already mentioned, or CFK for short, enables dependency calculation. So for every key in a system, commands for keys maintains an ordered history of all transactions that have touched that key. When a new transaction arrives during pre-accept phase, CFK allows to quickly determine which existing transactions this new transaction must depend on by looking up the relevant key histories. Without this structure, the system would need to scan through like every single command in order to find like things that are conflicting with the given transaction, which of course would be completely unacceptable. Commands for key also tracks current execution status of a given transaction. This allows to build accurate dependency graphs that also avoid unnecessary waiting on the transactions that have already been completed. So if the transaction has already been applied, you don't really need to wait for it because, I mean, well, it was already applied, so you can proceed with your own execution. So once transactions are fully applied and no longer needed for future dependency calculation, their entries are safely removed from the CFK, preventing unbounded memory growth while preserving correctness. So next one is a configuration service. It manages cluster membership and topology changes, serving as a bridge between the external configuration management and Accord's internal coordination. Accord requires a linearizable source of epochs to ensure consistent ordering of its own topology changes across the cluster. And we are getting this from TCM, or transactional cluster metadata, if you're not familiar with it. This is something that we have added in 5.0 last year. Which notifies Accord about metadata changes. So Accord converts these TCM representations into its own internal topology structures. So Topology Manager is also responsible for something we call topology readiness. The service tracks when metadata is known, when the cluster is ready to coordinate new transactions, when it's ready to handle reads and writes for a specific epoch. So the configuration service also propagates the changes across the entire cluster, ensuring every node receives and acknowledges the new configuration before transactions begin using it. And this also precludes disagreements in like topology. And finally, it performs the topology garbage collection, safely removing all topology versions since they will not be needed for later transaction processing or for recovery or for anything else, for what it's worth. This prevents unbounded growth of topology metadata. Here I tried to sort of like represent the way the topologies or ready topologies in a cluster are shown, and you can also see that different ranges may also be in different stages. So it can be like we can know whether or not the specific range was added or removed in a given topology, and can sort of like reconstruct the end state of the topology using this information. So the journal replaces the traditional commit log for all Accord transactions. Unlike our existing commit log, the journal is addressable and can retrieve individual command entries, or not only command, actually, all the entries which are persisted in journal can be later retrieved. Topologies are also saved there, and they can also be retrieved as such. Journal records execution outcomes and command states throughout the transactional lifecycle. Rather than logging just mutation, like a traditional commit log, the journal captures the complete state transitions, which means that whenever we receive a message, we don't record the fact that we have received this message. Other than that, in contrast to that, we are writing the outcome of execution of this message on the command store. And in order to make this even more optimal, we're trying to diff the previous state of the command with the next step of, or next state of the command after the message application, and we only record the diff in order to keep the information that we're persistent to the minimum. So whenever the node is restarting, the journal is going to rehydrate the transactional metadata to restore the system to a consistent state. This bounce recovery ensures that partially completed transactions can resume where they have left off, and is a very, very important part of the transactional protocol. The journal performs garbage collection of redundant transactional states by fetching redundant before timestamps and checking whether or not it is safe to remove old entries, depending on whether or not they will be needed by other nodes for dependency resolution, application, or recovery. And we do not have a separate commit log for mem tables that Accord manages, which means that everything is really persisted only in journal. So journal has to get tied together with the rest of the subsystems in order to ensure that whenever the node is restarting, we also will get the data from the journal to the mem table, and later from mem table to SS tables as well. Now the progress log. So it is a subsystem of the recovery protocol. It is also described in the Accord paper. Its fundamental guarantee is that any transaction that is known by at least one healthy replica will always execute eventually and apply on all correct participating replicas, ensuring that the system maintains liveness under failure scenarios, like different failure scenarios. Progress log manages incomplete transactions and ensures they complete by monitoring their state. So it listens to safe stored or stored changes or transitions between different command states, and tracks how transactions progress through the life cycle from pre-accept to applied state. And when this monitoring finds that transactions aren't reaching stable status within the expected timeframes, the progress log attempts recovery. So it coordinates fetching of necessary states or whatever it takes in order for this transaction to move from its current state all the way to applied status. The next one is durability service. It tracks shard level and global durability guarantees across the entire system, and it ensures that transactions don't just execute, but also are safely persisted in the data store, which means that we need to survive the balances, and in order to do that, we need exactly that. And durability service tracks transaction durability across shards and replicas throughout the entire cluster. This helps the service to understand not just whether a transaction has been applied locally, but whether it has achieved the required durability across all participating nodes. So durability service listens to mem table flushes and tries to understand when the mem table has when the data from the mem table has been persisted on disk. And it also coordinates with sync points during ownership changes and bootstraps, and is trying to make the information from the sync points distributed or persisted in the, or not persisted, reflected in the redundant before structures. And durability service manages and updates collections such as redundant before that track the state required for garbage collection. And we coordinate the timestamps and durability status, and this enables us to perform safe cleanups whenever we need to purge something from the journal without affecting in-flight transactions. I think that this is the last one. So data store serves as a storage abstraction that holds the actual data modified by transactions. Unlike command stores, which manage the transaction metadata, the data store contains the real application data and is backed by the storage engine of Cassandra. Data store coordinates with the command store during transaction execution. When a transaction is ready to apply its rights, command store ensures that the changes are written in the correct application order. Data store also participates in bootstrap and rebootstrap. So rebootstrap is basically a special case of bootstrap whenever you repair in the case of loss of the log or corruption. The new nodes joining the cluster can bootstrap from a consistent snapshot, and recovering nodes can catch up on missed changes without requiring fetching entire metadata or entire data set. And finally, data store manages the durability contract through something that is called ensure durable. It's just a method call and reports the redundant before timestamps. The ensure durable call guarantees that committed data will survive crashes, while redundant before timestamps tell the system when the old metadata can be safely garbage collected, at least from the perspective of this node. So you can, in principle, as an operator or as a developer, whenever you're debugging code issues, inspect a cluster through the virtual tables. But I personally think that we should lower the entry barrier, and instead of forcing people to use node tool and virtual tables, we should make this information available in some form of control panel or a dashboard, which allows referential connections between entries without having to copy paste and remember a bunch of different commands which are sometimes inconsistent and hard to remember. I'm listing this just to show the things that you would have to memorize if I didn't do the work that I have done by making a UI that makes it possible for you not to remember any of these things. And of course, we couldn't just leave you without at least some command line fun. And whenever you are debugging the journal states, unfortunately, you will still have to interface with at least some of the command or command line interface. So there is a thing which we call journal dump tool. You can simply upload the jar with this tool to your node and then have it inspect your journal states. There are many ways in which you can interact with journal using this tool in case you think that the transactional recovery is misbehaving in some way. And of course, we don't anticipate any problems whenever we're going to roll out, but from whatever we have seen, most of the pain points were coming from a lack of progress. Therefore, I was trying to focus whenever creating tooling on making it so that progress would be both obvious and easy to track and find out. And as always, project readiness as GA is coming up. It's been coming up in 2021. It's still coming up, but I hope that not for long anymore. And my goal here, and my goal, I guess, not just here, but more in general, is to build community familiarity with Accord. I would like other people to get involved with Accord, get more comfortable with it, get more confident with it, and there are many things that you can contribute in. There are many low-hanging fruits in debug tooling, in documentation. I would like to invite collaboration. I would like to invite people to ask questions and maybe start poking around. And of course, we are just in time, 23 seconds to take any questions. Yeah. Thanks, folks. There was at least one question.
Hey, a lot of the process depends on timestamps. Cassandra supports milliseconds. Has it changed for this? Position of timestamp, is it changing?
I will try to answer this question. So first of all, the question was, Cassandra does support timestamps already. The current resolution is microseconds, whether or not this changes with the core. Sorry?
Milliseconds.
I think that...
Micro.
Yeah, micros. Thank you for nodding for me because I started doubting myself. Yeah, so micros, and this does not change. So the timestamps that are going to be written in cells in Cassandra itself are still going to be near real-time timestamps, not human-generated, which means that whenever you're past Accord migration and you are interacting with the cluster through Accord transactions, you will not base applying timestamps, but timestamps will be generated by Accord itself. They will still be in micros, but the timestamp that is written to the SS table is going to be execution timestamp, which may be slightly different from the original transaction ID timestamp. Does this answer the question? Yeah. The reason why the timestamp might be different is the conflict resolution, right? Because we can regenerate the timestamp because of the conflict, but in principle, you can still see the timestamps in Accord, yes. Chris?
I have kind of two follow-ups to that question.
Yeah.
One is that how do we deal with clock drift other than tell people not to have it? And how do we how does it deal with like item potency then do we just not have any? I guess with transactions we don't have any.
With I guess there is no idempotency. Each transaction once applied is applied, and there will be always strict order of transaction execution. So for instance, if you were to retry the transaction, I guess what you could do, I think that we had similar conversations maybe 9 years ago, or I don't remember, with including some other colleagues from DataStax, and the problem was back then with Paxos, and pretty much finding out the state of the transaction that has happened, but we as a client have not learned the outcome of it. Is this what you're asking? So because
never mind the idempotency question. I guess my question is more about the clock drift, I guess.
Okay, the clock drift, my best question, at least at the moment, is don't have it. We did not do any special tooling in Cassandra as of now that would allow you to detect clock drift or combat it in any way.
So it's absolutely required, but there's no monitoring.
It is not required in the same way as it is required in in Spanner, right? So it's like you do not need like true time or anything like that. So the Accord tries to build the causal order of transactions based on hybrid logical clocks, and even though paper does mention something called reorder buffer, which does rely more on sort of like inter-DC latency and real-time timestamps, I think that current implementation does not really require like super precise talks, and Blake probably wants to either correct me or...
I was just going to say that, there's no correctness required.
Yeah.
Oh, so it is okay. It is okay if we have like 100 milliseconds.
The only thing that can happen is it may cause your operation to take a medium or slow path if it intersects.
Okay. So it'll be slower, but it won't have any correctness issues.
Exactly. Yeah.
Okay. Awesome.
But I think that whenever we're going to have the reorder buffer, this even though the correctness part is not going to change, the part where we do need to have clocks more synchronized is going to be more important, right? Because then we will sort of like close the reorder window based on whether or not we think that all the transactions that can be in the window will be also closed. But since this is not implemented, I think that Blake's question is the best, or answer is the best. Yeah, and so like just to like, even though there was like, how do you do that even?
One screen.
Okay, it's
Can't do it on dual screen.
okay. So even though I had this in, I was trying to present it by simply, okay, I'm just going to disconnect. Even though I was trying to present it with the slides, this was because I wanted to avoid something failing miserably during the presentation. This is all available as standalone tooling as of pretty much this morning, and it is in the branch on Accord GitHub. And so the TLDR is that you can actually interact with a Accord cluster if the resolution of this thing would have allowed us to actually see it in action.
Right side, you can go full screen. Drag it over.
Drag
Hit
it
the
over.
green button. Keep going. Keep going.
Keep dragging it.
Yep.
There you go.
Green button. Hit the green button.
Hit the-
Yes.
Okay, so you can actually interact with the in JVMD test cluster, with the real cluster, and with the Accord burn test cluster using this tooling. And on top of that, you can record your burn test in JVMD test. And as of now, I didn't implement the real cluster recording. To be honest, I don't think it's going to be very feasible, but in principle possible. So yeah, you can also generate Lamport diagrams from your D-test recordings, and whenever you think that there is an issue with the protocol, or you would just like to understand what specifically is going on inside of Accord, you can make a recording. It has filtering. It has you can see all the transactional states. You can see like whether or not we have taken slow path, fast path. You can see all the dependencies, and all of this is going to be hopefully shipped with together with Accord, and we will try to make it as accessible as we can for everybody to make their Accord learning journey more pleasant, I guess. Yeah, if you are curious to learn anything about that, I will definitely be available at least until Sunday, so hit me up. And besides that, I'm always available online and will be happy to answer any and all of your questions later as well.